thanks everyone for coming. We have the pleasure of hosting Rob today. He's coming to us from Oxford today, where he's ICL fellow. And Rob's told me that this is some new work he's worked on, and he's looking forward to explaining in great detail to us. So this is very disjointed from what we've done before, which is what I much more to do. So I'm really looking forward to seeing what you've picked up, and let's welcome Rob.
Thanks very much. Okay, so to sort of motivate, I guess, what I'm going to talk about today, in a lot of problems, there's some sort of notion of symmetry that arises. So here's an example just to kind of like keep in your mind. So imagine you have a situation where you've got images of cats and you're trying to output basically a binarized image where it's a black pixel if it's a cat image. Okay, so you take this thing as input and you produce something that looks like this as output. Intuitively, if you first of all take an image of the cat and then translate it, and then get the binarized result. We are unmuted, I believe. Maybe they can't hear it. Are you? Shall I just continue in the meantime and try to express? Okay, so if you take the cat, translate the cat, and then get your binary image, that should be the same thing as taking your cat, getting your binary image, and then translating that. So intuitively, a property that you might want to hold. And there's sort of various other examples you can imagine in lots of different problems. Basically, anytime there's some sort of like geometric structure or some sort of like algebraic structure in play, like maybe point cloud data. This comes up a lot in, say, like protein modeling and graph structure data and problems like this. So how do you kind of formulate this? Like, how can we actually make this sort of precise, this property that we intuitively want to hold? Well, the thing that people talk about is a notion called equivariance. So basically, you say you have a function f from x to y. It is equivariant with respect to the action of a group G. It's basically when you take an element of the group G, apply it to your input to f, and then map it through. So that's the same thing as, first of all, getting your element x, mapping it through your model, and then applying G to the output. So in the example of cats that I gave earlier, here x would be the set of images, f would be a function that takes an image and produces like a binary image as output, and G would be the group of translations. So it's saying translate your first image, map it through your neural net or your model or whatever, however you're defining this. That's the same thing as then taking your image, mapping it through, and translating the results. But there's a problem here, which is basically like this is intuitively something we want to hold. But in practice, like this won't hold by default. So if you just take a neural net and train it on images of cats, it won't necessarily follow that the resulting model actually has this translation equivariance property that we want. So the question of how you actually enforce this. And I guess it's kind of an instance of sort of a more general problem, which is of interest, which is basically how can you impose some sort of like top-down algebraic constraint on a model that you want to hold but won't necessarily by default. And there's kind of two approaches that you can use here. So I'm going to talk about these now. The first is what you might call intrinsic equivariance. So basically, this sort of characterizes actually the majority of approaches to equivariance in the machine learning literature, at least. And basically, what you do here is you define essentially a set of primitive equivariant components that you use to make your model overall. So you define a set of equivariant linear layers, say if you're using a neural net model. You define a collection of like equivariant nonlinear layers, and you take your overall model to be some big composition of these sort of small primitive equivariant components. And you can check that equivariance is preserved under composition. So the model that you build in this way will necessarily be equivariant as a result. But this is quite a natural idea, and as I say, this is what the majority of like the geometric deep learning literature does, if you're familiar with this. But there's some problems with this. So it turns out that this approach, at least to date, has demonstrated it needs quite a lot of hand engineering for each case. So for each group that you're interested in, each group action that you're interested in, so how it transforms like the images, you need to do something quite different in each case, basically. And so you end up doing a lot of kind of low-level hand engineering for each specific configuration. As a result, perhaps, Sorry, I'm gonna just, yeah. Yeah.
Let's try to play a double. Maybe we're gonna see if I'm gonna mute the this thing, and then maybe hopefully my computer picks up better the sound. But let me get this right. So I'm how do you get the controls on Windows or something? So, yeah, so mute that guy. Right, does this sound better now? Okay, that's much better. All right, so now you have it here, and you have the double act of that and that. And I'm so sorry.
No problem at all. Thanks very much. Cool. Okay, so yeah, so it's a natural idea. This intrinsic approach is quite natural, but it requires a lot of hand engineering, and perhaps as a result can be quite brittle at scale. So you might be aware that AlphaFold 2, which is DeepMind's protein generation model, prominently did use an intrinsically equivariant neural network in like its second version. But actually they got rid of that. In their third version, they found that basically just a completely unconstrained model using like a transformer architecture just scaled a lot better. And so even though it wasn't exactly equivariant, the overall benefit of having this more scalable architecture kind of outweighed that. So this is a bit of a problem with the intrinsic approach. Recently, there's been some, I guess maybe over like the last 4 years or so, there's been interest in what you might call symmetrisation. So these approaches kind of take a different approach. They basically define a procedure that takes as input essentially an unconstrained model. So it's not equivariant. And it does something to it, and then produces an equivariant model as a result. And here, essentially, the idea is you want your model F, basically, you want to treat that as like completely opaque. You don't want to sort of look inside it. You just kind of want to wrap it or do something to its inputs and outputs in some way that gives you the desired guarantee that you care about. So obviously, this is kind of interesting because it lets you use basically these more scalable architectures as kind of like this backbone, and then still get the equivariance property that you're interested in. And so how can you do this? Well, here's like an early example of a symmetrisation procedure. So this is called Genosi pooling. So imagine you've got a function that takes a sequence of n inputs and just gives you some real valued output. It turns out, you can convince yourselves of this probably fairly easily, that this function here, considered as a function of x, is always permutation invariant. So you start with your original f, and you basically, instead of returning the value that f produces for a given sequence, you just sum its output over all possible permutations of that sequence. And because you're summing over all permutations, necessarily this transformed function now will be invariant to permutations of the input. It's kind of that's sort of like the entry level idea that kind of gives us a flavor of how you might approach something like this. There's been a bunch of other examples. Here are 3 more. I won't go through these in depth, but it turns out that, you know, for various choices of these components here, this f, h, and p, starting with a general function f and some actions of some group g, these functions here all become equivariant with respect to those group actions, regardless of which f you started with. Even if f is like some really complex, you know, transformer, some, you know, very powerful neural network, it's still equivariant as a result. So there's some open questions here, which I'm going to talk about today, which is basically, the first is like, essentially, where do these methods come from? Like, what's actually going on here? And I guess the reason to ask that is not just for curiosity's sake, but also because you can then ask, you know, are these the only possibilities? Are there other things we could do instead of these examples? Essentially, these examples basically just kind of, you know, give the method and then state and show that the result is equivariant. But it would be nice to sort of characterize the space of all possible procedures of this kind, sort of choose one that you actually care about. Another question is, can we do sort of more complicated things here, like where if you've got a model that's sort of like partially equivariant, can you sort of like upgrade that equivariance? Can you sort of add an additional symmetry constraint on top? That might be something you're interested in doing. And I guess importantly for a statistics audience, what about stochastic models? This comes up a lot, like the protein example I mentioned earlier is a stochastic model. These methods that I just described work purely for deterministic like neural networks, basically. So, you know, there's not a theory of symmetrisation for stochastic models yet either. So I'm gonna try and address these questions for you today. I'm going to talk about 2 papers. The first of them is this one here. which basically provides sort of like a general theory of symmetrisation that also extends to the stochastic setting as well. And then just recently, we have submitted a paper to ICLR, which basically applies a sort of new methodology that came out of this theoretical work to diffusion modeling, basically for a molecular generation task at scale, and show that it works better than basically other methods. So it's something you can actually apply, and it actually scales up to quite large problems. Okay, so this first paper, the underlying theory of this is developed in terms of something called Markov categories. And there's a natural question that gets asked here, which is like, why do this? I'm going to explain what Markov categories are in a sec. I'm going to digress slightly and just sort of motivate this a little bit. We talk a lot about the model in statistics and machine learning, but I think actually there's kind of three models. There's like the mental model we have about the world, sort of in our head. We probably is like the most important model, really. It's our intuition for how things behave, how things are. Then we write down like a mathematical model, which we, publish and put in our paper and so on. And then inevitably these days we write like code to implement sort of our mathematical ideas in a computational way, and sort of like separate from the mathematical model as well. And really, I would say at the moment, essentially all of these models are actually quite distinct. Like the maths that we write down has sort of like a rough resemblance to the mental model. And then the computational model can look quite different from both of these as well. And it's natural to sort of ask, like, why is this the case? Potentially you've had the intuition that you feel that this is the case sometimes. Why is this actually the case? And I think arguably for probabilistic settings, a major reason for this is measure theory. So, this is in theory what all of our probabilistic reasoning is ultimately justified in terms of. But it's really complex and sort of hard to work with. And so in practice, like we actually try to basically avoid measure theory as much as possible. We often do things like writing down this kind of like ad hoc sort of density notation instead, which is kind of more lightweight and flexible, lets us ideally convey more of what we mean, in a sort of more lightweight way. And this works kind of surprisingly well. But inevitably, we end up having to write things like this. This is a little bit of a caricature, but probably it's not as egregious as I think everyone here, myself included, has written something that looks something like this at some stage. You've got like Z repeated twice here. You've got X 3 times. You can kind of make sense of this, but it's not really precise anymore. It's really we're relying on having sort of like a shared understanding of what things mean rather than the actual symbols rigorously referring to things that we think they do. This is basically imagining like sampling from a conditional VAE, passing through like the encoder and then back through the decoder. But anyway, and so this can actually make things more complex. Despite our efforts to basically simplify our notation, simplify our lives, this actually makes things more complex. And as evidence for this, here is the proof that one of these earlier methods of symmetrisation that I showed you actually does give you something that is equivariant. I'm not going to go through this. And I actually think this is really the best possible proof you can give using this density formalism. But I would claim that this is not an intuitive explanation of what that method is doing. On top of that, it's also not explaining kind of where this method comes from. It's just literally proving that it gives you something equivariant. It's not explaining how this arises in a natural way. And if you wanted to extend this to cover these more complicated settings that I mentioned, it's really hard to do. So we need something better. And I claim that Markov categories basically take an alternative approach to this kind of density notation. They essentially abstract away these kind of painful technical details, but they actually maintain rigor. So you're still saying something that's mathematically completely precise. You can be very, very exact about what you're saying, but you also don't need to worry about this low-level measure theoretic stuff. You end up with a theory that's very lightweight and visual and closer to the mental and computational models that you actually implement. And it basically becomes more conceptually scalable. We talk a lot about like computational scalability, but I think conceptual scalability arguably is as important these days as well. It's kind of like programming in Python versus programming in assembly, but for maths. There's a lot of claims. Let me try and back that up with some like proof. I'm going to give just a brief example, a brief introduction to what Markov categories are, and then I'll show you basically how I use them. So the first step is like, what is a category? You might have heard this term before. Essentially, it's nothing scary. It's just something that models a collection of entities that behave like functions. So if I give you a bunch of functions, there's not really that much you can actually do with them. There's sort of 2 things you can do. you've got compatibly typed functions, like if you've got a function that returns an output in Y and then a function that takes an input in Y, you can always compose those two in sequence and you can get a, the composite function G of F. It's one thing you can do with functions. Something else you can do with functions, well, it's sort of not something you can do. I guess it's something that functions like exhibit, is like there's identity functions. There's functions that basically take an input and just do nothing. And that's really it. So a category is any collection of entities for which these two properties hold. So basically, in the language of category theory, you would say that these X, Y, and Zs, you call them objects. You say you have these arrows, F, G, called arrows or morphisms. I'm going to potentially split between both terminologies. I'll try not to, but I might say either one or the other. And these satisfy the axioms that I just mentioned, that you can compose compatibly typed arrows or morphisms, and there are identity arrows for each object. And that's it. That is the definition of a category. And there's a bunch of examples. You're familiar with them already without realizing it, perhaps. The classic example is the category set. The objects of set are just sets, and the arrows of set or the morphisms of set are just functions. These obviously satisfy the axioms I just mentioned. Another example is the category mes. The objects of this are not sets anymore, but measurable spaces. And the arrows in this case are measurable functions. And it turns out that if you compose measurable functions, you get something that's also measurable, so you end up with a category. Right. For probability, probably the most important example of a category is a category called stock. So in this category, the objects are now, again, measurable spaces. And the morphisms from X to Y aren't functions anymore, but are Markov kernels. You could think of these basically as conditional distributions or stochastic maps. You've probably seen this definition of a Markov kernel before. It's a sort of function that looks like this. It takes a measurable set and an input and gives you a probability. I'm not going to worry about this today. The point is you can formalize what a Markov kernel actually is. I'm going to just draw them like this. So it's some sort of, a Markov kernel is like basically a black box that you give it, you read this sort of from bottom to top. It's a black box that you give it an input in X, and it gives you a random output in Y. So it's got kind of like an internal random number generator inside it. It takes an X as input and just spits out a random Y. And that's really all you need to kind of know about Markov kernels for today's talk. I'm going to use these diagrams quite a lot. They're called string diagrams. They may seem potentially scary initially, but actually you're quite used to string diagrams already. I think probably many of you will have seen this diagram before. This is like the transformers architecture. This is a string diagram, and most machine learning papers and really papers from many different fields will have diagrams that look like this at some point, where you essentially read it like a flow chart, basically. Again, also in this case, from bottom to top. And the string diagrams that I'm going to use are basically going to be things that you can read in exactly kind of the same intuitive way as you would informally a diagram that looks like this. So yeah, basically try to use that as a way to kind of interpret these. Yeah. So I guess like there is a category of Markov kernels, and they would definitely call them that when they're talking about that specific category. I guess I'm introducing one specific category here, but then we're going to zoom out and just sort of consider abstractly things that behave like that, if that makes sense.
Because I wouldn't think of the kernel as something that gives an element, takes an element in X, spits out a random element Y. I would think of the kernel as what you've done there, but takes an element of X and a set Y and gives it the probability.
Yeah, but I mean, when you implement that on say you're implementing an MCMC algorithm. Sorry, I'm trying to market this, but
I think of that one as like got an element of X and some element for another space.
Yeah.
And you put those together.
Yeah, so I mean, you can still formulate that as a morphism from X to Y. You've got flexibility in terms, like the arrows don't have to actually be functions, but it's a help. I think it is a reasonable interpretation to say, like the Metropolis kernel takes as input your current position and spits out randomly your next state. That is how you kind of sample from that kernel. I guess indeed, you can take other perspectives of what a Markov kernel is, but you can interpret it as essentially a generative process or sort of a sampling procedure that gives you a random Y as an output. I think it's reasonable.
Yeah, I think I mean, mine intuited they put the nonlinear space basically all over. Like a random function, it's very random. Take your current state, then you take some random noise, you put them together with a deterministic function.
Yeah. So I mean, well, that would give you a Markov kernel,
Yeah.
but like this is giving you, this is like a Markov kernel where you don't worry about how that F and that noise is generated, basically. Like,
You basically don't want to put that space.
yeah, it's like, so, you know, it's basically just, all it is like the kind of measured theoretic, the sort of rigorous version of this notation here. It's just something that you give it an X, you can think about it as defining a distribution on Y in kind of a deterministic sense, or you could think about P of Y given X as something where you give it an X and it just spits out randomly a Y. There's sort of two sides of the same coin, but I'm going to emphasize the sampling perspective more in this. So, and maybe this next bit will be helpful in that sense. So given two Markov kernels, if the output of one Markov kernel matches the input of another, you can always obtain a composite Markov kernel that basically looks like this. Okay, and so how do you sample from this Markov kernel? Well, you first of all take an input in X, little x here, you plug it into K, you get a random output in Y. You take that random output Y and you plug it into M, and you get a random output in Z. That's sort of something you can do if you're ever given multiple Markov kernels. Formally, this would correspond to the Chapman-Kolmogorov equation, but we don't need to worry about what that is today. On top of this, there's also the identity Markov kernel. So given any measurable space X, there is a kernel that basically takes as input X and just returns the same element in X. Essentially, deterministically, it's like the Dirac kernel at its input. You just return the input that you're given. And so it follows that Stoch, in this sense, is indeed a category. You can compose Markov kernels, and you have identity Markov kernels. Given pairs of Markov kernels between any four spaces, essentially, you can get a Markov kernel between the product spaces. You can sort of stick these things side by side and consider them one Markov kernel, where they take an element in X tensor U. I'm going to write this tensor notation here. This just means basically the product space of X and Y. So it's just pairs of X and Y. So it takes as input, sorry, X and U. It takes a pair of an element in X and an element in U and gives you a random pair, one element of which is in Y and one element of which is in V. So to sample from this, you're given these little X and U's, you sample independently from K and independently from V, and then you stick the result together and you return that. It's kind of the natural thing you would think when you look at this diagram. Great. And on top of this, I'm just going to state this. There are also Markov kernels that let you swap, copy, and delete information. So there is a Markov kernel that takes a pair as input and just deterministically returns you the same pair as output, but like reversed. There's a Markov kernel that takes as input an X and deterministically copies that and returns the pair. And then there's a Markov kernel that just throws away its input. Okay. Two last conventions. So Markov kernels you can think of as like conditional distributions, but you can also talk about unconditional distributions in this framework as well. So if you want an unconditional distribution, you can view that as a Markov kernel out of the singleton set. So it's a Markov kernel that takes just basically one input that you know already and just gives you a random element in X. And we're going to draw that with like these triangles like this. And on top of that, you can think of deterministic functions just as deterministic kernels as well. Like think of them basically as degenerate Markov kernels that degenerately produce a single output. Okay, now this is like the formal definition. I'm not going to go through this and doesn't actually matter that much what it means. But my reason for including this is that basically there is a way to kind of like abstract this definition in a very precise sense. So you can kind of like, you can talk about all of these things and it means something very rigorous and precise. So yeah, there is this notion called a Markov category. It has a precise definition. Practically, what a Markov category is just any collection of entities that behave like Markov kernels in the sense that I defined earlier. So you have some objects and morphisms. Okay, you can compose these morphisms in sequence and in parallel. And you have basic information flow for like swapping orderings of things, copying information, and deleting information as well. So essentially, like you can kind of take my word for it, once you have this definition here, you don't need measure theory anymore. You can kind of just show that basically Markov kernels exhibit this kind of algebraic behavior, and you can just entirely work with these axioms that you stipulated without ever having to go down to the level of talking about like sigma algebras and X's and Y's and things like that. You're just literally manipulating things in just the same way as in linear algebra. It's traditional to talk about abstract vector spaces without worrying about like the specific instantiation of that vector space that you might study in a particular application. Yeah.
Very much.
Yes.
Is there anything that's really that's different fundamentally from looking at functions and measure value space?
I mean, so you
So
could,
the space of sign matrix, like this,
Yeah.
and it's like the probability matrices set in there.
Yeah.
And you just think about functions acting on space of measures. You can efficiently have identity. You can recover Markov. So I was wondering what's the fundamental difference.
so I think if I'm understanding your question correctly, you can view a Markov kernel as a deterministic function that takes as input X and returns just a probability distribution on its output.
And then X would be also thing. So measure value transformations would be functions that takes in things in space of probability measures or space of sign measures, then returns to something else like sign measures. So
Yeah.
things that are done by say specified points and all this probabilities working at random functions. That's typically the way that people formulate.
Yeah, I think so it is closely related. I think essentially it's a very similar idea, but you would rather, for applications, you would rather think about a neural network that takes as input point X and gives you an output rather than a distribution on X. You want to give it some specific image and then get an output. But indeed, it's very closely related. We can talk about that after. Yes.
Also, tell me something. Is it possible for your string diagram to loop around?
No, so everything is sort of feed forward and just goes up the page, basically. Yeah.
So right now, what you said is like we take the Markov kernel, like they're talking like the joint distribution, the marketization, competition, and the Markov category. Isn't that the classic category? And Markov category, like
Yeah. So
what you described
yes.
is more preceding than the Markov category, right?
So I just described one specific Markov category, and then I'm saying, so this is Markov category of Markov kernels and measurable function and measurable spaces. Now I'm saying a Markov category is just any category that behaves like that sort of concrete instantiation in the precise way that, I mean, roughly that I've just described. So you can compose things but indeed you're right, like under some conditions, like any classy category on a suitable monad will give you a Markov category in a quite general way. And actually, like here's some examples. So not every Markov category is the one that I just described. Like you can kind of instantiate, you can find other examples of Markov categories that sort of, have more specific properties that you might be interested in. I just described the Markov category of measurable spaces and Markov kernels. There's also a Markov category where the objects are standard Borel spaces and the morphisms are Markov kernels, and this is kind of better behaved in some ways, so it's possibly something of interest in some applications. There's a similar one for topological spaces. You have continuous Markov kernels become the natural notion of morphism. These can be recovered as suitable classy categories as well, yes.
Yeah, about this one then, is there a way to use these Markov categories to also include the null set information that you originally had? So sometimes you don't care about those, like in the classic category, but like if you have a space, sometimes the fact that you have a particular set which are measure 0,
yeah,
it's kind of important. Are you able to, is there like a Markov category that also takes that into account?
There is a notion of almost sure equality in Markov categories, so I think possibly gets to what you're saying. Yeah. It won't matter for this, but yes, indeed, there's ways you can talk about these things. I'm just going to kind of go through this a bit quickly because I'm aware of time. So those top three are sort of something that you might think are natural for talking about probability theory, but other Markov categories exist too. These bottom three examples also turn out to be Markov categories. These are all kind of like less interesting because every morphism is deterministic. So possibly less interesting from the perspective of doing probability theory, but anything that you prove in a general Markov category automatically holds in all of these cases as well. So it's basically like your theory is now, it's kind of like when you write code, you want to ideally write your code to apply in an abstract way to kind of as many things as possible. And then it's considered sort of good software engineering to sort of instantiate your code only concretely sort of later in the process of developing it. It's kind of like the same approach here as well. You want to develop your theory in a sort of abstract, kind of high level sort of visual language. And then when you need to instantiate it specifically in particular concrete settings, you can do that after the fact later. You don't need to worry about the details of like sigma algebras for developing sort of the initial part of your theory to begin with. Write once, run anywhere, basically. Okay, so there's a question here, which is like, what can we actually do with this that's like new? Can we actually get like new methodology from this? There's examples of Markov categories being used to describe sort of retrospectively things that like already were known, but can we get some new methodology for this? And the answer is yes, and that's basically what I'm going to talk about. That's what I talk about in this paper here. And actually, if this is, you know, potentially interesting empirically, this is not something I did sort of retrospectively. It's actually kind of how this work was produced. I didn't set out to kind of like find this new methodology. I was doing some stuff with Markov categories, and it sort of naturally arose by basically having this more general kind of abstract perspective. You can kind of see things that are really harder to see when you're down in the weeds at a lower level. So, I mean, that's, you know, take that as you will, but there's sort of empirical evidence that this is profitable as well. In order to kind of talk about this, remember, like the goal here was talking about symmetrizing neural networks. So we're going to kind of like specify, roughly speaking, what we want to do here is to talk about symmetrizing a morphism. You can think of this as like a Markov kernel in a Markov category C. That's kind of like the goal that we're going to set ourselves here. In order to be able to do that, we need a way to talk about groups in this abstract setting. We've kind of thrown away all of our sort of traditional theories, so we need to kind of like rebuild it or sort of generalize it in some ways so it applies here. There's kind of a natural way you can talk about groups in this abstract setting. You can say a group is just, it's not a set equipped with some multiplication and inversion and identity operations. It is just any object G equipped with morphisms that look like this that satisfy the group axioms. So this one is multiplication, or you think of as multiplication. This one you think of as identity, and this one as inversion. And as morphisms, like the meaning that these take actually depends on which Markov category you're in. So if you are in the category of sets and functions, then these actually become sets. These actually become functions. In MES, they become measurable functions. So you might have heard this notion of like a measurable group. You sort of recover that for free, basically, by defining a group in this general kind of way. You need some axioms on these morphisms. You can specify these in diagrams as follows. So this is an axiom you've probably seen before in group theory. This is just basically saying you've got associativity. It's saying if you take two inputs here, the second and third input, multiply them together, and then take the result and multiply that by the first input, that should give you the same thing as, first of all, multiplying these two inputs, getting the result, and then multiplying that by the third input. It's literally just kind of like associativity of multiplication in the usual sense. You can express that just diagrammatically. The other group axioms you can also do, this one is saying that if you take what you're thinking of as your identity element, you multiply that by an input, that's the same thing as just doing nothing. This one is saying if you take your input and you basically copy it, you invert one copy of it and keep the other copy the same, and then multiply the result together. That's basically just giving you the same thing as the identity element. So it exactly corresponds to unitality and inversion of the group multiplication in the sort of traditional context. So groups in the category set are exactly groups in the classical sense, but we can talk about these things more generally in any other Markov category we want. Great, so the last component we need, we've got groups and their operations. We also need to talk about actions. So remember, an action is something like take an image and like rotate the image, or take a cat and like translate the cat. We need a sort of abstract way to talk about this. Basically, we're going to just say it is some morphism alpha that satisfies these axioms here. So if you first of all apply alpha once and then apply alpha with potentially a different G, second time, that's the same thing as first of all multiplying the two inputs together and applying that to X. And this corresponds to this axiom that you've probably seen in group theory as well, which is associativity of group actions. Similar thing for unitality. If you just apply the identity element to the input, you just get the input back. Great, so we've got a way to talk about groups and actions. I'll just skip over this one. We're now at a stage where we can talk about equivariance in quite a natural way. So we can say that a morphism X to Y is equivariant with respect to these actions if basically applying the action and then applying K is the same thing as applying K and then applying the action. Just basically, you can swap the ordering of K and alpha in this sense. And if you instantiate this in the context of sets and functions, this is exactly recovering the initial definition of equivariance that we started with. So here we're saying for all G and X, take any G and X, apply the action, so hit X with G, and then map that through K. That should give you the same thing as basically taking X, mapping it through K, and then applying the action G to the output. It's sort of exactly the same thing as we had previously, but we now recover basically for free kind of like a suitable notion of equivariance for Markov kernels as well. And if you think about what this means in Stoch, you are led to this definition here. So you can say that a Markov kernel now is equivariant if when you take an input G from the group, apply that to the input X, the kernel that you get out, or the distribution over outputs that you get out, is basically the same thing as the push forward of K by G. It's the same distribution as you get. I've got an image here which maybe is more helpful. So it's like you can imagine your Markov kernel takes inputs in X and produces a random element in Y. Let's say that's distributed according to this Gaussian looking thing over here. So this notion of equivariance that I just wrote down is basically saying if I give you any input X, you look at the distribution over outputs that you get as a result, and then you apply the group action to that distribution, you translate basically the whole distribution. That should give you the same thing as basically, first of all, translating the input and then looking at the distribution of outputs that you get. It's very analogous to the cat, but now we've got basically the action is happening essentially on the space of distributions of your outputs rather than in the output space directly. Why? Does that kind of make sense roughly, just visually? Yeah. Cool, so it's a natural notion of equivariance. It turns out actually, so what people do in the literature in machine learning, they define equivariance as this, but they define it in density notation as this. To me, this is not very clear, like, why is that equivariance? Sort of, equivariance is something where you give it an input, where you do something to the input and something happens to the output. There's no, like, why is G on both sides here? But people have kind of worked with this because this is the natural way to talk about things in the context of densities. But once you sort of step back and you analyze this in terms of kernels, you get a much more, I think, natural definition out that actually turns out to be easier to kind of work with. And it has this kind of visual interpretation as well. Okay, so just to recap, we've got a way now to talk about groups, actions, and equivariance in a general abstract Markov category C, where we can instantiate that now if we want to talk about, measure theory or any probabilistic setting that you care about. You can basically talk about all of group theory actually at this level of abstraction as well. So there's other notions defined in the paper that are useful too: homomorphisms of groups, orbits, cosets, compactness, semi-direct and direct products as well. It's all sort of suitable generalizations that give you quite a rich language for talking about this theory in this kind of abstract setting. So you don't actually lose very much by zooming out in this way, at least for this application. Okay, so now we can talk about symmetrisation procedures. So I'm going to just state this. This is kind of a fairly natural result. If I give you any group in a general Markov category C, there is always another Markov category CG defined as follows. So the objects of this category CG are now pairs of an object in C equipped with an action of G on X, sorry. Basically, you can think of these, if you've done like some group theory before, these are like G sets, essentially objects equipped with an action rather than just objects kind of floating around freely. And the morphisms in this category CG between, now remember the objects of these pairs, so we need to define what is a morphism between this pair of objects, this pair of pairs, basically. We're going to say a morphism of this in this category is something that is a morphism in C that is equivariant with respect to alpha X and alpha Y. So previously between X and Y, we had sort of all the morphisms there. In this category CG, we're going to just have the morphisms that are equivariant with respect to the actions that were specified. And it turns out that this is also a Markov category. You can show this, the remaining components, you've got to actually define these as well. Like there's other things here too, there's other structure in play, but these are also naturally inherited from C. So in general, for any Markov category, you always get another category CG in this way. Great. And so now we can actually give a definition for what a symmetrisation procedure actually is. So in the literature, it's kind of not really defined what this is. It's basically the results are stated as like, take your function f, do this particular thing to it, and I'm going to check that this thing is equivariant. Here we can actually give a very concise definition of what a symmetrisation procedure in general, in kind of the abstract sense is. So we're going to say it is just any function sim of this form here. So this is kind of a standard notation people use in category theory, where you denote the set of morphisms from X to Y in a category C as CXY. So this is like all Markov kernels from X to Y in your base category. They're sort of completely unconstrained. The symmetrisation procedure takes as input one of these and produces as output a morphism from this thing to this thing in CG. So if you remember what the morphisms of CG are, these are morphisms that are equivariant with respect to alpha X and alpha Y. So this is a function that takes as input an unconstrained Markov kernel and basically upgrades it to become equivariant with respect to these specific actions here. Sort of all the information that you need, all the sort of relevant kind of objects in play here are all kind of depicted. There's like the base category you're interested in. Are you interested in Markov kernels? Are you interested in functions? There's the actual objects in your category are these, X and Y. There's the actions and the group, all depicted compactly in this kind of one definition. And I think there's sort of no loss of generality here. It's sort of hard to think of a more general definition of what a symmetrisation procedure is. Okay, and this is very general, but actually we're going to be able to characterize every single function of this form in a meaningful way that we can actually implement in practice and recover all of these previous methods. And it's potentially surprising, but it actually turns out to be possible. And the result that lets you do that is this here. So remember that CXY is the set of morphisms from X to Y in C. So the set of Markov kernels from X to Y, or the set of functions from X to Y, depending on what C is. It turns out that for all the choices involved, for any group, for any action, for any X and Y, there is a bijection of this form here that basically sends a morphism X to Y. That's an element of this left-hand side. So this morphism here on the right-hand side. So notice there's this G popping up here now. So this is now something that takes as input a pair of G and X and produces a Y as output. So this morphism here that is like the image of this thing here is going to be a morphism that takes a G and an X corresponding to the G and the X here and produces a Y as output. It turns out that things that look like this correspond bijectively to things that look like that. Okay, so why is that the case? Well, I'm not going to explain like why that's true. It actually is not. It's something you can show with like relatively elementary kind of means. There is a kind of fairly nice categorical story of like what's going on here. There's this notion of an adjunction in category theory, where basically, yeah, you can kind of, there's this sort of, it's sort of a very natural thing that once you do some category theory, I know this is going to sound really like, it's not the best argument for it, but basically this is sort of something that comes up a lot, and it turns out to apply in this particular instance in a way that would sort of, you would be naturally led to kind of posit this result, having set things up in this way. It's hard to kind of convey that without more background, but that's kind of, you can take my word for it. This doesn't just sort of come out of nowhere. Great. What's the consequence of this for our purposes? So the main consequence that this has is that every symmetrisation procedure that we're interested, that every symmetrisation procedure as we've defined it can be expressed as a composition of these two steps here. So remember, a symmetrisation procedure takes as input a morphism from X to Y, and it produces a morphism from X to Y that is equivariant with respect to alpha X and alpha Y. It's just any function that has that form. Every procedure of this kind, no matter how crazy or whatever that it may be, can be expressed as, first of all, applying this bijection that I just showed you, and then applying some function in the second step. Why is that the case? Well, this is a bijection, so you can basically think of these two sets as like the same. So any function that goes from here to there, which is, that's a symmetrisation procedure, can be expressed equivalently as a function that goes from here to there. They're the same set. They're in bijective correspondence, so that's every function. I don't know if this is clear to people, but it's kind of that's the sort of result. So there's a natural question then of like, what can we actually, we know how to implement this first step. I've just given you that is this bijection here. So what can we implement for the second step? We need to sort of actually choose something in practice to actually use for our implementation. There's sort of only really one choice you can make here without more assumptions. So the second step, just remember from the notation, is a function that takes as input a morphism from this thing to that thing and produces one from this thing to that thing. So it takes as input something that looks like K sharp here. The only real way that you can get from K sharp to this thing is basically by precomposing K sharp by some choice of omega. So you choose some omega that goes from this object to this product of objects, you take your K sharp, and then you just basically output the composition of those two. And just looking at the input here, the input is X alpha, the output is Y alpha. So this has the right type on the right-hand side. It is equivariant with respect to these actions, just from the fact that you're dealing with a category. And so the composition of morphisms is also a morphism as well. Okay. Yeah, so that's literally the next slide. So yeah, there's a sort of natural condition that you might want to hold here, which is that if you're given an input to your symmetrisation procedure that is already equivariant, the procedure should do nothing. It turns out that if you want that to hold, your omega needs to have this form here. So it basically needs to not modify its X input, just needs to sort of map that through, and then essentially it reduces to a choice of gamma. So I'm going to just, I realize this is a lot of like, there's a lot of layers of abstraction. So let me just make this concrete. So what I'm saying is that like, essentially every kind of procedure that you can define without further assumptions can be expressed in this way here, where you first of all apply this bijection, that kind of earlier result that I gave. So that takes your K as input and maps it to this Markov kernel as output. And now you need to turn this thing into a morphism that takes just an X as input instead. And the only way really without more assumptions that you can do this is by precomposing this thing on the left by this morphism at the bottom here. So notice that like this top part, this part here is like the same. See, all I've done is plugged in this bottom bit at the bottom. That's just precomposing that middle thing by this omega from the previous slide. All right, let's instantiate this now concretely. If we instantiate this in the Markov category set, you get a result here, which says that if you've got a group acting on sets X and Y, and you take any function K, X to Y, and then any omega that is suitably equivariant, then you get an equivariant function of this form here. And this turns out to recover one particular method that people have used in the literature. It's one of those ones from the list I showed you earlier. But you can actually get something new here as well that people hadn't discovered, which is kind of cool. And this is a procedure for stochastic symmetrisation. So you can actually symmetrize Markov kernels directly rather than symmetrizing functions necessarily. And that is this result here. So we instantiate that result I just showed you before in the category of Markov kernels and, of measurable functions and Markov kernels. We get a result that says if G is any measurable group acting measurably on X and Y, you've got to add in all these caveats, but they come automatically from the fact that we have a Markov category. And if you have any Markov kernel and any stochastically equivariant gamma, where G acts on itself by left multiplication, then the following sampling process here defines a stochastically equivariant Markov kernel from X to Y. So you first of all take your X, sample your G, plug it in. It's basically just, I'm gonna just, sorry to go back, I know it's a bad thing to do in a talk. It's basically just reading off the sampling process here. Start with an input X, copy that, get a random output gamma, then convert that, plug it into, apply that to the input X, and then you also pass that through and apply that to the output. Why you can basically just kind of like read off the sampling process using essentially the rules that I showed you earlier, and it comes out to be, thank you. At least take my word for it that that's the case. But then notice something that is kind of, this is sort of a downside of using like this measure theoretic language as opposed to this general Markov category thing. Like really, this is not technically precise in a sense. We've already kind of, even though I've tried to be kind of precise here and convey what's going on, like this sampling process here doesn't describe a function of this form here, where if you actually really wanted to define a Markov kernel in the rigorous measure theoretic way, you need to actually technically write down a function that looks like this. So in a sense, it's actually easier to just work with Markov categories and just draw these string diagrams rather than committing yourself to essentially this particular instantiation. Anyway. I'm going to skip over this last bit in the interest of time. Basically, you can, this is giving you something that is stochastic. You can actually enforce this to be equivariant if you want by applying an averaging step at the end. If this is of interest, we can talk about this afterwards. I'm just going to briefly mention, there's a bunch of extensions that are in the paper that really, I guess, bring out kind of the benefits of using Markov categories. It's not just that it sort of lets you describe this sort of base case of symmetrisation, but also lets you then extend to getting sort of a whole new kind of suite of different methodological possibilities that are really just too hard to kind of talk about with this infrastructure. It even goes so far as to give you a way to get equivariance with respect to the full general linear group, which is kind of crazy, right? Like the full set of invertible matrices gives you a concrete procedure that you can implement. It's in the paper. That will give you a neural network that is equivariant with respect to any invertible matrix applied to the input and output, which seems like, I mean, yeah, it's sort of surprising that would happen. I'll just talk briefly about one application that is, okay, I guess there's a question here, but I'll answer that at the end. This is an application. Basically, we've just submitted this to ICLR. It will come up actually on arXiv tomorrow if it's of interest. So something people are interested in doing equivariant stochastic models for is for diffusion models. You might be familiar with this. Basically, the high level is they define essentially two Markov chains. They try to sort of align appropriately to model some data generating process. And often it's desirable to have this reverse chain be equivariant. Basically, you want these backwards kernels to be equivariant and the first kernel to be invariant. The reason that you want that is because when you do that, you can show that the ultimate model of your data that you're going to produce is invariant. This comes up, for example, in like modeling proteins or molecules, because if you sort of rigidly transform your distribution over molecules, really that should make no difference to like the distribution of molecules that you get. You sort of want it to be invariant with respect to rigid transformations in that sense. This is like, as I say, it was used prominently in the AlphaFold model, AlphaFold 2, and in a bunch of other applications as well. And essentially what people have done previously is they have ensured equivariance of this backwards process by using a model that looks like this, where mu theta is an intrinsically equivariant neural network. So it's a Gaussian distribution. It goes from ZT to T-1, and it uses an intrinsically equivariant mean function. And you can show that that gives you an equivariant backwards kernel. But then, as I said, like this thing needs to then be kind of quite like hand engineered at like a low level. You need to sort of really be careful that, you know, each component is equivariant, and it's potentially quite a brittle model, and I guess empirically has been observed today. So what we do instead is we basically just symmetrize a set of unconstrained backwards kernels. So essentially, instead of mu being, say, like a graph neural network or some intrinsically equivariant neural net, it can be anything. It can be a transformer, it can be something really complicated. We can leverage all sorts of highly optimized kind of models that people have spent years developing, and we can just symmetrize on top of that and still get the equivariance property that we care about, but without needing to go to this kind of low level of detail. In the paper, we derive basically a suitable replacement of the training objective people use for diffusions. And essentially, I don't know how familiar people are with diffusion models, but basically this is what the actual training procedure looks like. The only real difference compared with essentially a regular diffusion model is kind of like these two lines of code that's been introduced. And this F here is a neural network that you get to decide what it is. It can be, again, a transformer. It can be something kind of crazy. It's very unconstrained and very expressive and flexible. And by adding these two lines of code and then modifying this step here with these R's that you get a stochastically equivariant backwards process, but without having to use an intrinsically equivariant neural net for any of the components. Great. And you can think of this in practice, it turns out in a precise way as kind of like a learned data augmentation that you employ a test on, but I won't elaborate on that. Yeah, I'm going to just mention this. So we applied this at scale, and it turns out to work really well. We basically used it kind of like as a sort of drop-in replacement for an existing model that people have cared about, this EDM model. Uses intrinsic equivariance. The sort of fair comparison with that is our second SymDiff model here. This top one is like a much larger model, which we used. And essentially the criterion people care about is molecular stability. And we essentially changed sort of nothing else in their code. We kept everything else the same, but just substituted in our backwards process and jumped that up by like 5.5%, essentially for free. So it seems to work at scale as well as kind of in theory. And yeah, that's all of it. So thanks. I think
we have a few minutes left for questions for Robert.
One question, I didn't this be very well formulated. So here, if I understand correctly, we have a function which we want to, where we want the inputs and outputs to observe some algebraic axioms.
Yep.
Does this framework allow for you to have those axioms defined not in terms of the algebra, but then go back down to the lower level language? Could you say that I want to construct this string diagram with like an augmented function such that I'm somehow maintaining some behavior which is expressible not in algebraic terms, but in measure theoretic terms?
I mean, I guess like I'm not sure. So quite possibly, I think. Yeah, I don't know. I think you could probably. I mean, certainly you can express other properties than I've focused on groups and equivariance for this, but you could definitely consider other things as well. Whether it would be fruitful to do so if you really care about specific facts about measure theory, I'm not sure. But my claim, I guess, generally is you actually don't care that much about measure theory in general. I think actually people, they don't really care. Like it's not reality.
Yeah.
It's just like a model of reality. And really what you care about is this higher level kind of compositional behavior. And this sort of gives you a way to just talk about that behavior, this level of abstraction, and still say meaningful things that you can actually derive new stuff with. But yeah, there are certainly going to be things that you can't say if you really care about measure theoretic facts. You just can't see at this high level of abstraction.
And there are some things which I guess you can write for, like you showed the definition of symmetry in both lines.
Yeah, there's a notion of symmetry that like generalizes to this abstract setting that then instantiates down to what you care about. Yes.
Yes, actually, first one question, which was when you talk about the extension. So when we define this, for example, equivariant Markov kernel, we never really used the inverse of G, right? We had G on both sides of the equation, but we didn't have an inverse.
For which one? Sorry.
When you define, like, for example, push forward of a Markov kernel.
Yes.
Fine. So my question was, do you really need the element? So do you really need the group to be a group, or can it be like a groupoid?
Yeah. Well, so groupoids would have inverses. Monoids would not, and possibly is that what you mean? So you could definitely talk about a notion of equivariance with respect to a monoid. This result here would not be the case in general, because then there's the inverse coming in there. But yeah, there's definitely other extensions, yeah, for sure. Yeah, true. Okay. So I'll read it out. I'm not sure. So perhaps I'm just naive, but it seems obvious that the slide with a particular instantiation involving gamma and precomposing by a sampled group element will be a good symmetrisation, but it seems obvious. Presumably the novel part is the converse. Does that also say something interesting if one is not already invested in using category theory to do things? So I guess maybe if I'm understanding this correctly, perhaps Alex can clarify if I'm not. I think that essentially it is the converse. So the converse is kind of expressed by this result here, which is saying, I think the direction that perhaps you're asking about, which is that like essentially every symmetrization procedure can be written as, first of all, applying this bijection and then doing something in the second step. So effectively, if you then instantiate what that means, it's saying like every symmetrization procedure can be written as, first of all, apply this step and then do something here, which may not be precomposition. It's basically just apply this and then go to that step there. So if you're willing to allow any function there, then every symmetrization procedure can be expressed in that form. And I guess my claim is that really, without further assumptions, there's nothing other than precomposition that you can do. Like it's sort of the only structure that's available. You're going to need to say something more about your groups or your inputs and output spaces or actions if you want to do some function in the second step that is not precomposition here. You can actually kind of make that precise in using categorical tools. There is a notion of a natural transformation, and you can characterize all of these using something called the innata lemma, and precomposition turns out to be what that is. So effectively, in a very precise sense, it's sort of like the only structure available or the only method available without further assumptions. Yeah, and if you had further assumptions, you could use that. But I guess I'm not aware of situations where people like do, and this is kind of meaningful. And I guess particularly for a machine learning or like a general purpose sort of algorithm, you do want something that you don't have to make these additional assumptions. You do want something that's kind of general purpose. And this gives you essentially a way of basically describing that space of possibilities that is harder to see how you would do without categorical tools. But yeah, I guess potentially, I'm not sure if that answers your question or if Alex is even in the chat anymore. But yeah, possibly. Anyway, yeah, I don't know if there's other questions.
I think we're on time, but we will also go upstairs to our team and probably with Rob afterwards. So if there are any questions remaining, you can ask it then. Thanks, Rob.
How do I, it's like a dialogue. Let's have it. Oh, there we go.
Okay.